I'm Georgia, and Georgia is a full professor at KUIS as of late last April, and also affiliated with Hessian AI. She was an assistant professor there and an independent research group leader. She has secured the prestigious Emmy Noether grant from German Research Foundation, DFG, in March 2021, and she received her PhD from Technical University of Athens in Greece. So today she's going to talk about interactive robot perception and learning for mobile manipulation. We are looking forward to her talk. Thank you very much, Georgia. Stage is yours.
Thank you. Thank you very much for inviting me. So today I will present to you a subset of work from my group that targets mobile manipulation, that it is a problem that I'm very passionate about. I think that it is the next thing that we should focus on in robot learning. And I will try to convince you about this and why we should put our effort. So if you work in robotics, in robotic manipulation, I think we should put our efforts together to bridge the gap between navigation, manipulation, and of course perception. Okay, so if we look at humans, even at very early age, we will see that the kids usually interact with their environment. They try to understand how the world works, right? How their own body works, and basically what we see is this eternal loop of perceiving in order to act, and act in order to perceive. And by this cycle, we as humans very early on, we develop sensorimotor coordination. So we basically do also this hand-eye coordination. We understand our own body, what we are capable of. We develop skills, and we create a representation of the world. So we create this external representation of the world in which we act. And finally, we interactively explore and learn new skills. And this is a continuous cycle that happens in a human's life. Now, the question is, why don't we have this still in robotics? The points are many. Right, so for sure, one part comes from the lack of good perception algorithms, and of course, then how we can couple them with robotics. But obviously, also the hardware was not good enough in the earlier days. And now I believe that we have an opportunity to develop algorithms towards embodied artificial intelligence through mobile manipulation systems in general. And as I said from the beginning, why I like mobile manipulation systems, well, they combine mobility and manipulability, and they are equipped with multiple sensors so that they can sense their world around them. They have an increased workspace, so in theory, the whole world is their workspace. So they could reach possibly every space that a human can do. I have to note here that we could even frame humanoid robots as mobile manipulation robots. On every type of mobile base where a manipulator can move is a mobile manipulation system. So even an aerial robot with an arm is a mobile manipulation system. So we can now envision all the applications of these types of robots. But of course, the uncertainty and the difficulties that arise from combining manipulation with mobility are much larger. And what I propose in my research in order to basically unlock the path to robotic embodied intelligence is to leverage structure. And in this talk, I will focus on three topics. First, on how we can leverage structure in order to learn mobile manipulation coordination, how we can extract representations for mobile manipulation robots in order to interact with their environment, and finally how we can enable them to actively explore and act in open things, in house, let's say house-like environments. So as the first part of the talk, so I selected three topics so that I can maybe keep it short and we can have like longer discussion. The first part targets the coordination of mobile manipulators. So as I said before, mobile manipulators combine all these different embodiments, right? So if we see this robot that we have in our lab, the Tiago robot, it has two humanoid arms, 7 degrees of freedom each. It has a torso. It has a 2 degrees of freedom head and a mobile base. In this particular case, this robot has a differential drive mobile base, and it is equipped also with cameras and laser sensors and other types of sensors. Now, we can either try to solve this problem of mobile manipulation as a whole thing, but this becomes very difficult because you have a hyper-redundant robot. So you have like a 20 degrees of freedom robot when you try to just grasp an object, that it is a 6-dimensional pose. So you can understand that there is a big gap. So you have a very hyper-redundant robot, but you have too many constraints. This is the problem. You have too many constraints, especially when you are acting in the real world and you want to resolve not only collisions, but also, for example, time, efficiency in energy. All these are basically additional constraints that we need to add into our optimization ideally. So this makes it quite challenging to solve whole body control and whole body planning problems. So in a work that we presented last year in IROS, it was a RAL paper that was also presented in IROS and received the Best Paper Award in Mobile Manipulation. We consider to decouple this problem and consider basically the robot as a two-agent system in this particular case. So we didn't tackle all the embodiments of the robot in this work. So we considered just the base and the left arm of the robot, and we tried to coordinate them. And let me explain what I mean by coordination and what I mean by hybrid action space reinforcement learning that you see here. So when a human moves around, right, we move around and we want to go, for example, in this white table and grasp maybe the yellow sugar box. The human knows what is its own reach, what is their limit. So they know that they have to move close to the table. And once they are close to the table, they can now extend the arm and basically execute a manipulation action. We want to basically endow the mobile manipulation robots with the same capability. So the robot to understand its own reach and understand to take decisions according to when it can really manipulate an object or not. Therefore, we formalized a discrete action space where the discrete decision, sorry, a hybrid action space with a discrete part that is when should I activate my arm in order to execute a manipulation action, and the continuous part that is the optimal pose of the robot that it is expressed in SE2 based on the pose of the base. So the position and orientation of the base that also dictates the whole body pose, and it also correlates with the reachability of the robotic arm. So if the robot, for example, positions itself with its back to the table, it is evident that, okay, the solution space from a planning algorithm or an inverse kinematic solver might be difficult to reach the sugar box in this position, right? So how we try to formalize this problem, we try to use it in reinforcement learning so that we can reward the agent whenever it positions and executes a manipulation action correctly. And we how we deployed this hybrid action space, we basically define this hybrid policy that contains two components where the discrete part that you see here, the P theta D, conditions on the continuous actions that we take. And intuitively, if we think about the way that we define here the action space, the agent has to first position itself, so the continuous, take the continuous action, and then based on this continuous action, the robot should decide whether to activate the arm or not. And we can train this with our favorite deep reinforcement learning algorithm by also deploying a reparameterization trick. So we can model the discrete variable of the categorical distribution. In particular, in here it's a 0, 1, but it could have been any type of discrete distribution, and you can deploy the Gamble softmax reparameterization in order to formalize this categorical distribution and take gradients and do backpropagation in order to alter the parameters of this policy. Okay, so now we formalized the hybrid policy for this mobile manipulation scenario. And now we need to train it. So now we need to collect the data in order to ensure that the robot will understand its own reach, right? So it's basically understanding if I am standing here, can I reach this object to reach it? And select these kinematically reachable poses. Now, in classical robotics, how this has been tackled in the past, people would basically take the operational workspace of the robot. So what you see here is for the left arm of the robot, it's the operational workspace. This is quite easy to extract. So you put your robot in a simulator, you densely sample 6D poses in ellipses, or depending of course of the structure of the robot. Here you can see basically the reachability, the workspace of the robot. So you sample the workspace of the robot, and then you try to find how many IK solutions you can have, with what frequency you can find an actual solution given random initializations of the IK problem solver. So you create this kind of frequency map about your workspace, and what we can see with bluer are basically the areas that are better reachable for this type of robot, and you can see also the reachability on laterally. So now, because we're considering mobile manipulation robots, in order to understand how to place the robot in order to reach reachable targets, we consider that the floating base scenario. So we consider that the base can be moved everywhere in the space, and we invert the mapping of this operational workspace. So we invert this map, and then we basically slice it on the level of the floor. And by slicing it on the level of the floor, we get what we call the inverse reachability map. And note here is that in this reachability map, and in the original, on the original workspace, we can also include the measure of manipulability. So not only the IQ solution, but also an additional metric of manipulability that shows us also for manipulation how easy it is to continue manipulating an object if we place a robot in a particular location. So with this inverse map, we know that if we place our robot in the bluer areas, there is a chance of high manipulability to find a pose that would make our robot reach this 6D target that you see here with purple. What this means is that the robot will have to query for any different 6D target, we will have to query a different map. So with every 6D target, we get a different mapping on the floor on how we can place the robot. So usually how this was done, people would randomly sample 6D targets and then store them in a memory. And if, of course, you had to reach a target that did not exist in your memory, you had to basically requery and do IK solutions and so on. If you had obstacles around, you would have to cut out. So you have to do several heuristics in order to cut out the map. So, and also another problem is that this is quite discrete, right? This is not a continuous representation. So we thought, like, why don't we use this information in order to train a reinforcement learning agent, so to learn a curability map. So we use this data that we collected anyways by random sampling and querying and so on, and train a Q function on this base placement problem. And not only we can consider now the manipulability, so the overall readability, but the actual task success. So the reward function for this problem contains actually the execution of the reaching action. And you can see a completely different map. So the robot has many more capabilities in the end in actually placing itself and reaching the end goal rather than just discretizing and considering the overall manipulability, and we get this smooth readability map. So now we have this local map that it just tells us what is the next step that the robot should do, what is the next pose that the robot should take in order to reach this target. But this is very, very local, and mobile manipulation is inherently long horizon. The robot has to navigate an environment and find the targets, manipulate them, and so on. So we need to somehow deploy this knowledge about the reachability into a framework that can solve longer horizon problems and use it in essence as a prior, basically. And in order to use this prior knowledge, we proposed boosted hybrid reinforcement learning, that it is an algorithm that allows us to transfer knowledge from behavior priors and build more complex behaviors. So with boosting in reinforcement learning, that has been some prior works. You can find the references here. What we can do is that we can start from a base problem where we formalize as a reinforcement learning problem, and we solve with, and we learn, a Q function. We can then progressively transfer this Q function onto the next problem that it is of higher difficulty in theory, and don't train for a new Q function, but rather keep the prior knowledge fixed, so the prior Q function fixed, and learn only a residual over it. Therefore, you only learn what you are missing on representing well what are good or bad actions to take for solving a more challenging problem. And you can keep building on this. So you can keep building Q functions that are more complex by adding up the previously learned components. So the original Q function and the residuals of these tasks that are way more challenging, up to a point, of course, that you stop. In theory. Theoretically, you can add up as many as you want, and you can have the exact same representation of the original Q function. But what is now favorable in deep reinforcement learning is that usually when you have tasks that are very difficult and you might have complex reward functions, it might be very difficult with a single function approximator, with a single neural network to represent everything. So by modularizing and basically splitting down the problem into these residuals, you make your life easier. You make the learning easier, and you also can deploy already existing knowledge. So if you have learned already where should I position myself in order to activate my arm and do a reaching action, why should it be learned again when you want to, for example, grasp an object or navigate and then avoid obstacle if this has been learned already? In order to also facilitate the training of the critic, we have seen that it is quite beneficial to also update the actor. The actor is not transferred, so the actor is learned from scratch over these composed Q function composed of these residuals. But what was very beneficial is to add an additional KL regularization component where you reward, in essence, the agent for remembering actions that were good from your previous task. And this is why you see here this forward KL regularization. What is also very important in this framework that handles that basically represents the Q function as this sum of residuals, and that it doesn't really create residuals on the policy space, but rather on the Q function space, is that we can handle the problems of changing reward functions across tasks, and we can also handle the changing of the observation spaces across tasks. So if we keep building on prior knowledge that was simpler, and like initially you were just trying to understand how your body works, and then once you capitalize on that, you can add on manipulating objects, the observation space increases because now it's not just you, it's just you and the objects around you. So your observation, so your state augments. And this can be easily handled, this asymmetric information, while transferring to tasks of higher complexity can be nicely handled by this framework, because the state can effectively add on new information, while your residual can just keep looking at the part of the state that was relevant to its own part while it was trained. And the same goes for the policy. The prior policy can just take the part of the observation that was relevant for this particular policy, and you just train your new policy on the new observation space. So we started by just doing this reachability initially in this locality, the one step, basically motion and activating the arm and solving for the reaching task, having to navigate, then having to avoid additionally obstacles, then having different types of configurations, trying to grasp an object, not only reach, and different types of configurations, and also when there are other objects on the table that create clutter, and you have to find basically the clearance in order to grasp an object. And what is very interesting is that this approach can directly be transferred in the real world, because in essence we are planning, we are deciding, we are doing learning on a level higher than the actual execution. So we decide on poses of the robot and whether it should activate the arm or not. And on the low level, in order to execute this, you can deploy any controller or planning algorithm in order to resolve this. And you can also deploy this sequentially in order to do sequential pick and placing and rearrangement tasks, because the agent, if it knows its own reach, it is able to solve grasping, placing, and other types of problems. And currently we are extending this work to also consider a real contact-based manipulations, because you may keep requiring the high manipulability regions in order to keep manipulating an object. One caveat here was that if you train, of course, in simulation with a naive navigation policy, for example, this comes at a cost. So it increases the sim to real gap. So we had to basically tune our navigation policy to resemble the one that we used in simulation. But this also can be resolved if you use the same exact strategy that you will use in the real world for moving the robot around in the room. Is there any questions so far? If there is no, okay, I will continue to the next part. I just wanted to give you just a bit of intuition about also when we want to do this whole body control, basically coordination that I was describing in the beginning of the talk, we may even assume that we have some skills that we have learned, that we have designed, for example. And if we look into classical robotics again, we will see two types of ways in order to control our robot. The one is these reactive robot motion controllers that usually when we design them as like operational space controller, they are computationally cheap. They are having high frequencies, But the drawback is that they are quite myopic, so they don't have this look ahead. They cannot predict how the environment might change so that they can arrange their strategies accordingly. And on the other hand, we have these planning-based or look-ahead motion generation strategies where we can provide feasible trajectories with higher success guarantees, but the drawback is higher computational load and low control frequency compared to these reactive motion controllers. So very briefly, I will go through this because I think it's interesting, it might be interesting to some people. So if we consider that our skills can be represented as basically energy-based policies or in general, that they belong in the exponential families. That they are a distribution that belongs to the exponential family. Then it is very easy to compose these kind of skills, right? Because we can just add them up, the components of the exponent, and create what we call a product of experts, basically, which can be represented as a policy that is composed by other prior skills, and which is weighted by a temperature parameter or a weight in general that handles how much contribution each expert has in this superposition. And then if you want to query an optimal action, you can just do maximum likelihood and extract the action that basically maximizes the policy. One caveat here is how do you choose this temperature beta or weighting parameter beta according to the way that your environment changes. And for that, we have proposed two different ways of handling this problem. The one is probabilistic and the other one is basically optimization based on optimal transport. So if we frame the problem of selecting the best possible beta parameters for adjusting the importance of our expert according to the environment or according to the time step that we are in the environment, we can very easily frame it as a planning and difference approach and plan on the parameter space. But then what is also interesting to see is what happens if we formalize this problem as an optimal transport problem, where we consider that every skill is not just an expert, but it is a single agent. So we consider that we have multiple agents, like an agent that is reaching the goal, an agent that does obstacle avoidance in this particular 2D scenario, but in more high-dimensional scenarios, you may even have like style-based skills that you have learned from demonstrations, curling actions, and so on. So by deploying a Sinkhorn-like entropic regularized and balanced optimal transport algorithm, what we can do, we can compute the transport map of that you can see here according to a cost matrix that relates to the problem that you try to solve, which is like to reach a target, and adjust these beta parameters, as adjusting the transportation map in an optimal transport problem, and adjust what is the contribution of the different expert agents. And as you can see here, we have also some entropic terms so that we can ensure that we are equally sampling in the beginning all the agents, so that we can ensure that we are trying to transport all of them. But we also add the KL regularization also in this problem to relax the optimization landscape, and also ensure that we are not turning on and off experts abruptly. What is interesting here with this unbalanced optimal transport is that you can completely switch off experts. So whenever an expert is not needed, you can actually completely turn it off. Of course, the optimization decides on that and adjust the other experts appropriately. And you can be extremely reactive and very, very fast, actually. These optimal transport methods solve optimization problems in milliseconds. So you can actually handle uncertainty by being extremely fast in your decision making. You can also deploy it on a 7 degrees of freedom arm, and even having moving obstacles. And eventually you can also transfer it into the coordination of mobile manipulation and some weird tasks that we wanted to show here, but we are very excited about this approach of multi-agent optimization for mobile manipulation robots or humanoid robots in general. So I will move to the next topic that has to connect mobile manipulation to perception as the first step, on how, when we wanted to understand how we can represent the scene geometry in order to learn to interact with the world. So in general, our robots have to act in environments that there is high clutter, and classical basically approaches in SE3 grasping in the clutter do not really handle partial visual information. They usually have to scan the whole scene and then start querying for 60 graphs. They usually do not use a single view unless it is just a top-down camera that observes a single tabletop environment and does some sort of 4D, usually grasping. And for sure, many approaches are basically overfitting a single camera installation, and they cannot be used at any random viewpoint. But in mobile manipulation, we need to be able to have to handle partial visual information. We should handle single views, so the robot sees the scene and already knows, okay, I have to grasp this object, I have to go there and grasp it, and not just start querying around. And it should be able to handle any random viewpoint. And here you can see an example of random views of the robot in our lab with different installations of the scene. So in our recent work, this is quite ongoing. We reimagine grasping as rendering, as neural rendering. So what do we do in this approach? So we train a neural network that consists on the first pass by a convolutional occupancy network that takes a zip with a 3D TSDF grid of the single view of the scene. It parses it through and extracts a 3D feature through a 3D convolutional encoder, and trains then an occupancy network that tries to reconstruct the scene, and this is trained easily by this binary classification problem of 0, 1, of whether a point belongs on an object in the scene or not. So we try to do scene reconstruction, and then we try to leverage this 3D feature volume in order to do grasping. Now, once we have this occupancy network, we can go here and we can create scene rendering of the scene, deploying virtual cameras and doing gray marching and querying the occupancy network to understand whether whether a point from the camera belongs to an object or not. So in essence, we can create a new point cloud compared to our initial partial point cloud that is more complete because we have done this scene reconstruction. And now we can query graphs. We use a geometric approach for querying graphs based on point clouds. And then for each graph, we go additionally and we do neural rendering as if the graph itself was, let's say, a camera. So we want to see what does the graph see in the locality of the objects in order to extract features, local features that represent the 6D representation of this graph. And then we can train a graphic network that can classify graphs as good or bad on a scene level, so not on an object level. So if we go and look a bit more in detail, this is what I have already described, how we train the occupancy network. It's quite well known, and it allows us to get the scene completion, and we can query also at any resolution our scene. So we may start with a very rough TSDF and increase the resolution or vice versa. But of course, the question is how we can extract the right features for grasping. So usually in grasping, what is happening is that either you have a generative model that just tries to, by a variational autoencoder, for example, query grasp. So it does basically the grasp sampling approach, and then you have to have an additional evaluator network that evaluates whether or not this grasp is good or bad. When you do grasp detection, you assume that you have some broad sampling strategy than like the one that I described, the one that it is a geometric sampling strategy on point cloud. And then you need a network that can evaluate if the graphs are good or bad. However, usually this evaluation in the 6D space in SE3, it's quite difficult. So what is usually happening is that you try to evaluate the pose, so the 3D vector, and then you try to regress. So you basically query TSDFs, the voxels of the TSDF. You try to understand if the voxel contains a good grasp or not. And then after doing this classification, you try to regress in SO3, the 3D rotation of the graph. And this is also quite challenging because doing regression in SO3 and also depending on the different representation is quite challenging. What we propose instead is to extract features that represent directly the 6D pose, and we do this by this rendering approach. So we render the scene, we sample graph on the new point cloud that we get. We can arbitrarily create as much dense scenes as we want. So we don't need to rely on the initial, rough point cloud, but we can make even more dense point cloud. We can even sample on this new point cloud with additional constraints of reachability or semantics if we know about affordances and so on. And then we select each graph, and in each graph we place 3 virtual cameras on these 3 sides of the grip, and we do local neural rendering that we also supervise locally, trying to extract neural SDFs. So we try to we try to additionally. Can you hear me? Sorry, I thought my connection might have been dropped.
Yeah, we do hear you.
Okay, sorry. So we can additionally extract local features via this local surface rendering and extract these grasp relevant features that we can then use in order to learn how good a grasp is or not. Additionally, this local rendering comes with the benefit of getting a bit better also scene reconstruction, although this is not actually the real our real target in this work, but rather to extract better features for representing graphs. And how this pipeline looks like. So we take a single view of the scene from a pre-graph pose. This is the scene point cloud. We render the scene, then we do graph sampling, then we pass the graph. So we do this local rendering per graph, we extract the features, we pass them through the network that judges which are good graphs, and then we execute graphs sequentially. And here you can see the simulated setup. This simulation setup comes from an earlier work from 2020, if I'm not wrong, from the volumetric grasping networks. That was the one that was doing this classification of voxels that I was describing. And here, as you can see, with the red is the reconstruction, yellow as the sampled graphs, and green are the good graphs. And compared to other approaches that are completely implicit in 6D or semi-implicit, in the sense that they are implicit in evaluating the pose and they regress the orientation, you can see that we achieve state-of-the-art results in this benchmark, also in other data sets. And we can also transfer in the real world. And here you can see a decluttering action of the robot. Here we don't move the robot, we just have this single view. We re-render and requery every time that we move an object, and we basically obtain a new scene. But we can also move our robot around, change the camera height because we have the torso. And additionally, we can also select with which arm it makes sense to execute the grasp, given that we have a bimanual mobile manipulator robot. I don't know if there is a question so far, otherwise I will move to the last part.
Can you hear me?
Yes, yes. Hi,
Uh,
Fatma.
yes, right. Is there any benefit to have a detailed 3D model like from nerves over occupancy fields? Is there any,
Uh,
something very detailed?
Sorry, can you say again the question? If there is a paper?
If there is any benefit to have a very detailed 3D model from nerves, for example.
So it is similar to nerves what we do, right? But on the other hand, we assume that having the color rendering irrelevant to the grasping actually. If this answers your question. So in essence, what we do here is similar to observe. So basically, you do just the surface rendering without caring about colors. Also because, in my opinion, if you have objects with different colors, it can mess up basically your graphing pipeline because graphing is quite a geometric problem. So you really care about surfaces and local geometries. So in this case, doing a true nerf, let's say, with the color rendering might mess up in some sense the features, for example, that you are trying to learn. You add an additional complexity, let's say. If we assume that knowing also the color, in particular during the graphing generation, I mean, it is necessary and it's not something that we can append, by doing some RGB, I don't know, open vocabulary, object detection cannot be handled elsewhere. I think that it is not really needed. The color in this kind of pipelines, I don't think it's really needed for grasping.
I see. Is there any other way that you can think of, like a way of incorporating semantics, basically, better than color, maybe, beyond color?
So the extension of this work that we are currently working considers parsing and trying to do semantic reconstruction of the scene. And through the semantic reconstruction, we are actually trying to predict additionally affordances for the graph. So not just grasping generation, but additionally classification of the affordance, of the grasping affordance. So basically, if you have a knife, what is the usability of the knife? So you need to do a handover. So if you need to do a handover with the knife, you want to grasp it uh, um, from the cutting area and not from the grasp area. So if you want to cut, you need to grasp it from the grasp area. One issue that we have encountered so far is that there are not really good enough grasp affordance datasets with 3D models. There are affordance datasets, general affordance datasets. There are also in like ShapeNet. A lot of these objects that they might have like random affordances, like chairs that you can sit, for example, or like other stuff. There are some datasets for articulated objects, in which case you just care about predicting the articulation of the object, but the general grasping data set with different functionalities about the different objects. So for example, buttons with where should you grasp if you want to pour, or this kind of basically types of grasping affordances, they are quite scarce. So now my students have collected a subset of, I think, of 3D affordance net and ShapeNet. And he created an affordance data set so that we can pass semantic information. What we currently don't see quite easy is to create something like joint open vocabulary segmentation network plus graphing. What happens also now in the robot learning community, usually people just query separately with an open vocabulary model, and then you, for example, do grasping on the highlighted, let's say, object, which is trivial to do. I will also show you, like in the next work, we also used like a semantic detector decoupled from the actual execution.
Thank you.
Thank you. So the last part, maybe I'm a bit late. I will try to be fast. The last part has to do with active exploration, but also execution by mobile manipulation robots. So we already discussed about mobile manipulators, that they have to act in unstructured, cluttered environments. They have to use ideally only their embodied camera in the same way that humans use only their eyes. I think that it will not be really nice to have robots in houses and have additionally multiple cameras, right, in our houses to inspect us so that they can help the robot. So the robots would need to actively perceive and explore in order to obtain this task-relevant information under occlusion. And one question that we have in mobile manipulation compared to just a navigation for the purpose of scene reconstruction is, when do we have enough information so that we can stop the exploration and execute the manipulation task? So mostly in active perception, you will see mobile robots moving around, just trying to do scene reconstruction, and the goal is to represent as well as possible the scene. And even for grasping with static manipulation, the range of motion is quite limited. The scenes are quite small, while in mobile manipulation, the scenes are larger. The motion that the robot might do for reconstructing the scene is more costly, and we don't want to do wasteful motions. We want, once you detect the object of interest that you want to manipulate, you want to execute the task. So we need some sort of time and energy efficient solutions for mobile manipulation. So we consider a setup where we have, again, our robot with its embodied camera, and the robot doesn't know anything about the scene. The only information that it has, it's a rough, quite large approximate target area with this represented with this red bounding box. It only knows that roughly there is an object that it has to find, and some instruction like pick up the object at the right corner of the table. So the robot now has to explore the scene, build the TSDF of the robot, a volumetric representation, and then do active perception and grasp detection in order to understand that now I have found the object of interest and I can grasp it. Here we didn't couple it with the scene reconstruction of the previous work. Ideally, we would like to somehow bring these two works together and somehow explore uncertainties from the previous pipeline inside active perception. But for now, assume that there is no really network that can complete the scene. So the agent has to really sample candidate paths towards the area of interest, this red bounding box. Again, remember that we don't know the rest of the scene, so we broadly sample base poses and camera poses towards this target area. The grass poses are sampled based on an approximate estimate of target reachability based on what I presented in the first part of the talk. And we formalize this problem as a descending horizon control problem, or as like as a model predictive control problem, where we try to execute the best path, trying to balance two utilities, two objectives. The one is the information gain objective, and the other one is the executability of a possible grasp. So we try to collect as much information as possible, given the TSDF and the camera poses that are going to take in the next pose, but we accumulate this cost, this utility along the path. So it is not only next best view, but it is across a discretization of the path till the final goal that we sampled. And therefore, we also found it very beneficial to actually penalize to the distance that the robot actually travels in order to accumulate this information. And then on the other part, we have the executability objective that tries to sample graph. Initially, of course, there might be no graph because you have not found your target object. But once you have, the object becomes part of your site. So if you manage to go close to this target area, you can start query grasp, and you can query their reachability. Additionally, you can query their affordability, for example, if they really belong to the object that you want to manipulate, because they may be grasped on an irrelevant object. And again, we try to penalize the actions that the robot will have to do in order to execute the grasp. So how much will the robot have to travel from its current location in order to execute the grasp? So we try to make everything quite efficient. And the fact that we are doing this in this descending horizon or MPC style control allows you to reactively replan at every time step, as long as you get like new 3D scene information. In some sense, we can see this a bit like model-based reinforcement learning, where the model is basically the scene reconstruction. So the robot tries to build up the scene information and then stop whenever it has found enough information and grasp in order to execute the grasp. So here you can see an example of this approach. So the robot samples poses for its body, so the motion of the base, and in particular the motion of the head and the torso. We assume that we don't move the arms because it is actually irrelevant. As long as you don't have to manipulate something, it is just a waste of energy to try to solve a case already before being in the scene. And also, you don't know exactly if there are collisions because you don't know the scene. So the agent samples, and it can also do collision avoidance. So we can add additional objectives of collision avoidance. And here you can see the two utilities with light blue. So with pink is the TSDF that has been already discovered, and with light blue is the TSDF that you expect to find if you move to a new, here in this green, basically head poses, basically. And this is the executability that contains possible graphs and the reachability, not on the ground. Here we represent it on the agent space for both arms in this particular case. So here you can also select which arm to use, the one that has the highest reachability, in order to grasp the object, compared to the first work that we were only considering the one arm. And we have also seen that in particular, if you consider affordances that are necessary to act on sideways, so to do side grasps and not only top-down grasps, having this balance between information gain and executability, kind of a exploration exploitation basically balance, really affects the performance of the grasp of the robot. And ideally, we would want to place the robot in a location that it can already execute the grasp, and that the robot doesn't really have to do additional steps on deciding how to place now my body in order to grasp. So we try to balance everything in this single pipeline, and it is quite different to doing next best view, that it is very myopic again. So it's like the robot jumps around in order to collect enough information. As you can see, it goes randomly around the table without being oriented to the task that it has to solve, compared to our approach. And again, it was almost easy to transfer it into the real world. And now I assume I forgot to add an additional actually video here. So you will see only one execution. So we did several attempts with our robot. We have quite a very nice high success rate also in the real world. However, this comes with various challenges, because as you move your robot and you want to collect information while your robot moves, the noise in the real world in the base affects a lot the camera, as you might expect. So here you see, of course, ×4, I think, execution of the robot. But in several steps, we had to basically discard some frames of the TSDF. So we were not updating the TSDF at every frame, but we were discarding several of them. So as a takeaway message, to not take much more of your time, what we have seen is that we can do efficient mobile manipulation if we just consider the coordination of multiple embodiments, and not necessarily try to solve the whole thing as one, although this is needed if we just want to do whole body manipulation tasks like open opening a door and so on. Neural geometric representations are necessary for skill learning, and efficiently coupling the geometry of the body of the robot with the geometry of the scene is necessary. And there is this crucial interplay of perception and action that we try to find the right trade-off. And I believe that once we find this connection between how to perceive in order to act and then act in order to perceive, we will have the perfect balance to do way more challenging tasks with mobile manipulation robots. So yeah, thank you for your attention. And if you have more questions at this point, I am happy to answer.
Any questions?
I have some, if it is okay. Like,
Sure.
hi Georgia, this is Çağatay Bastogan. Thank you.
Okay.
This was a very nice talk. I really enjoy it, and it's a very interesting work. And I also like the name of your lab, Pearl. I think it's a good name to remember it. So my first question is related to the reinforcement learning that you presented. So
Mhm.
if I understand correctly, you do that learning. I mean, RL agent learns the reachability based on reachability, right? Like,
Yes.
but like you may like, so it's like in terms of basically the position, but how about the control of the forces, which is like manipulability? I mean, you mentioned it slightly, but I miss it. Like maybe you also consider it in the maps.
So the maps consider manipulability, but we don't consider exerted forces in this work. So this is like part of the basically manipulation policy in particular. So as I was saying, while I was presenting, we are now extending this work into a perception-based approach where we can effectively coordinate the manipulation of the arm while exerting forces, for example, when manipulating articulated objects, for example. This has to be added additionally into the problem. So here it is quite kinematic indeed still. All the tasks that I have shown here are quite kinematic, and they are not contact rich, where you have to additionally handle the exerted forces by the robot in the environment.
All right, thank you. I mean, like, I guess learning can be done by both considering reachability and manipulability together, right?
Yes, yes. You can add it as a reward function, basically, on your, yeah, you can add it in the reward as a reward, as part of your reward function, in order to promote, to go towards areas that increase manipulability. Of course, again, you have to scale the reward in the reward function. So if the task, for example, is to open a door, the manipulability has to be much higher so that it can promote posing the body of the robot in a position that will make it easier to open, for example, a door. Yeah.
Okay. Second question is the second part of the work. I work in the area of haptics, you know, human and machine haptics, and I'm wondering, like, can you provide us some? I mean, if you, you're not working in the area of haptics, but like, what do you think could be the role of haptics in this interplay between perception and action, like in terms of grasping objects or like putting on a table, you know?
So actually, this is quite interesting because yes, haptics is a very important part as a sensing modality for robotics. I don't believe we will
Which is most
be
of the time is ignored. I think that is yeah.
it is ignored. I think we don't have good enough sensors to really get the exact feeling like a human, right? So the classical works would consider that the force torque sensor can only understand, let's say, the exerted forces, but this is enough if we, as I was saying before, like open, close a door. You can get like the normal and okay, some tangential forces, but then you don't really know what is happening inside the hand. And it is quite interesting because yesterday I was teaching graphing to in my lecture, and I basically took them from the analytical model. Everybody was expecting that I'm going to talk for deep based approaches, and just in the end, I just told them some deep learning approaches. So the overall discussion was that with deep based approaches like perception, camera-based, let's say, approaches, you can only get the quality of graphs or sample graphs. You don't know if the graph can be maintained, and you don't know if the graph is stable. The moment that you have grasped the object, there is no guarantee that this graph is actually good in terms of force closure, for example. And for that, you really need to have feedback. So the question is, where does the feedback come from? So we really need to see whether or not with tactile-based sensors. There is quite some work now in some robotics labs for developing new types of tactile sensors that are quite cheap. They are vision-based also. So they have like cameras in the fingertip, and then there is like a gel soft material trying to resemble like the human fingers. But they are also challenging because, for example, you cannot do any type of grip. You have to be very delicate. You cannot exert any type of force with your fingertips. And in general, this is also for pinches, it's not for power grasps. For example, for many tasks you have to do power grasp. So also this kind of things you cannot really do with two-fingered grippers that we use. So definitely haptics is very important to be coupled with perception. And actually I have a student working on multisensorial reinforcement, robot learning, as I call it, for this kind of robots, so to try to understand how we can couple more information. But yeah, if you have any idea of any other way of extracting haptic feedback from interaction, even with the two-fingered robots, I will be glad to hear.
Okay, we can talk maybe sometime later. Like,
Yeah, sure.
but thank you. That's very detailed
Thank you
response.
too.
Thank you.
Any other questions? Georgia, I have one about the last part. You said that reconstruction is like model-based RL, right? But
more or less, if you were learning the model, right?
constructing the whole world is very difficult, right? Like, can you make it more
Yes.
reconstruction? Do you have any ideas about that?
Yes. This is quite interesting. So what we are trying to consider in ongoing work, while it is quite challenging, so I don't have any results to show you. Even in a single room with a few furniture, it is quite challenging to create a representation of this whole scene so that the agent also can use it for manipulation. So what I currently aim for, and I believe, is something that is also inspired by humans. So humans, we create different types of maps. So I think that we should have some sort of coarse and then fine representation. So the coarse representation could be either a very rough voxelization of the word that you can try just to represent maybe as an occupancy, like these feature volumes, but it can also be just a topological map. I am quite sure that having a high-level representation as a topological map is very, very important. But then I believe that on the low level, we need fine-grained neural representations, these geometric representations that these ones that I was describing, had more local fine-grained geometric representations that are relevant to the task that you have to do. So I can imagine that if the robot has some sort of representation of the scene, that should be possible semantic topological representation. So I know that I am in the kitchen. I am now in front of the fridge, of course, with some uncertainty. We have not talked about uncertainty at all, and I think that uncertainty is super important also to leverage. Now I have to handle the fridge, and then somehow you have to trigger these models that represent your interaction with the fridge, and also this kind of local representation, let's say, of the fridge in your in your view. So you will, we as humans always have this kind of mental models about objects, but when we interact with a particular object, we focus on the specific part of the object. So I think that this is very, very important for more large-scale mobile manipulation, let's say.
Yeah, sounds very exciting.
Let's see if it will work.
It has potential. Thank you very much, Georgia. This was
Thank you. Thank you too.
yes, well. Bye. Thanks, everyone. See you next week.
Thank you, Georgia.
Bye-bye.
Bye.